Dr. Sultan. Good morning, everyone. We are Hearing with the Eyes, where our project is to assist the hearing impaired during the COVID-19 era. Just go over a brief outline of what we'll be talking about today. We'll introduce ourselves and talk about the motivation and description of our project. We'll discuss some related theory, dive into some hardware and software design, talk about testing. We'll go over project completion and a cost breakdown. We'll show off a demonstration of our project, and then we'll go over some additional background information such as code standards and constraints, ethical issues, engineering complexity, and then we will take any of your questions. My name is Wyatt Matei. I am the team leader and software lead. I have an expertise in coding as well as project management.
My name is Kevin Zhang. I'm part of the software team, and my expertise is in software development.
I'm Kieran Clifford. I'm the hardware lead, and I have an expertise in electronics and hardware management.
And I'm William Barker. I'm part of the hardware team with experience in electronics and power systems.
So as a brief top-level overview, our goal was to design and implement a low-cost mask and app to aid hearing impaired people that will help hearing impaired people during the COVID-19 pandemic and in environments where masks must be worn. A big help that hearing impaired people often utilize when they're out in public is facial expressions and mouth movements when communicating with hearing persons. A big part of this was taken away. That mode of communication was taken away during this era, just because of masks. They cover the mouth, they cover a lot of the face, so that type of body language was really taken away and hampered. Other solutions do exist. However, there are caveats to them. They're not widely available, they cost too much, or they don't completely solve the problem. For example, the donut robotic C-face is a kind of all-in-one solution. However, it is not available to all markets. It's really just only available to Japanese markets, as well as the fact that it's really only in its Kickstarter phase. It's still in that weird Kickstarter phase where you can't really get your hands on it. Google Live Transcribe is the transcription side of the solution. However, it's not the mask side of the solution. And the Razer mask is kind of another all-in-one solution. However, it is prohibitively expensive.
As Wyatt had just said, our main purpose was to create a mask that would be able to help people with hearing impairments with the inability to be able to lip read or limited ability to hear people. And the way we accomplish that is using the Arduino Nano, which has a Bluetooth chip on the microcontroller, which we take the microphone signal and send it to the user's cell phone, where he can see what has been transcribed through our app that we've developed. This is just a diagram breakdown of what we have going on for our project. You can see the user will speak into the mask like normal, and the microphone will pick it up, and the Arduino will then process the signal and send it over to the app, where the user can read what has been said to them or they have said themselves.
So as Will had said, a large part of our project is transcribing speech into text. And the way that we're doing this is by utilizing Google Speech to Text API. What's really great about Google Speech to Text API is that it uses something called recurrent neural networks. And this allows the API in our project to work at a really, really high rate of accuracy and be incredibly efficient. But the great thing about recurrent neural networks is that they use memory cells that remember data and connections. What this means is that Google takes in tons and tons of speech transcription data, and they use it to train their API in this model. And by doing so, these memory cells are able to remember the data that they've been given and that have used this data to learn. And so, when a user puts on the mask, and the recurrent neural net already knows, it's seen this stuff before. So it's trained on a data set that can remember and make connections to previous data and allow us to transcribe speech really, really accurately.
So as you can see here, we have our hardware layout. And you can see that the inputs for the Arduino Nano are a 150 milliamp hour battery going into a 3.7 to 5 volt boost converter. And the microphone input and the outputs are the speech being sent to the phone via Bluetooth Low Energy and the status LED. And on the next page, we have the breadboard view of the circuit that we used and the schematic view of the circuit that we used. And then we have a view of the completed circuit on the breadboard with the battery, boost converter, and microphone. And on the right, we have the entire circuit integrated into a mask with the flexible perma board that we used. And as you can see, it's dispersed in the mask. So we went through a couple of iterations to fine-tune the hardware side of the design. Iteration 1 had a coin cell battery and a separate on-off switch. We upgraded the coin cell battery and removed the on-off switch. In iteration 2, we used a 3000 milliamp hour rechargeable battery, which we upgraded, and a 3.7 volt to 5 volt boost converter, which we kept. In iteration 3, we switched to a 500 milliamp hour battery, which we kept. And then in iteration 4, we switched to a flexible perma board to allow for more mobility and better contouring to the face.
So this is our app user interface. On the left, as you can see, this is one of our first iterations of the application. On the right is the most recent up-to-date version of the application. So initially, our application user interface was composed of just a placeholder text box where our transcribed text was to be placed, and a button to send the user to the Bluetooth settings, and a generic name for the application. Now, as you can see, we've improved the user interface, improving the appearance of the application, made our transcribed text area, a mic button, and a Bluetooth display. To provide further details on our application, the text box is used by the speech-to-text API to transcribe text, which can be transcribed in multiple languages, as it does have multi-language support. The mic button in the bottom left-hand corner of the phone, as can be seen, is used to activate the speech-to-text API, which will then start listening. The Bluetooth display located at the bottom of the screen is used to indicate whether or not the Bluetooth device is connected. And finally, the Bluetooth button, which is used to send the user to Bluetooth settings in order to connect the Bluetooth device to our application. So here is our corrective actions table. Here you can see what failures we had experienced and what corrective actions we had conducted. So the bad color scheme, which we had initially dealt with, was corrected by researching color palettes that accommodated for colorblind individuals, which we implemented into the application. There was also speech-to-text not working properly, which we corrected by debugging the data flow. The transcribed text being too small, which we resolved by auto-sizing the text with a minimum font size. And then one of the major issues of the application being that it constantly crashed after transcribing text, which was corrected by recreating the transcribed text box to accommodate text input from speech-to-text API. So here is an example unit test, which we tested the speech recognition functionality in our application, testing to see if the text is successfully transcribed after activating the API. This we broke down into 3 separate steps. Number one, pressing the mic button. Number 2, speaking into the mic. Number 3, letting go of the mic button. And as you can see, it all passed without any issues. So here is our integration test in which we connected the Bluetooth microphone to the phone in order to test the application and confirm that the status LED worked and successfully connected to the application. And again, it passed without any issues. Here is our acceptance test in which we tested the speech-to-text API to ensure that the accuracy of the transcribed text is greater than 90%, as this is one of our engineering requirements that we strive to achieve and was found to be greater than 90%. So it passed without any issues. And finally, here is our emulated app performance, which was obtained through the app profiler in Android Studio. As you can see, there's a large initial spike in the CPU, memory, and energy usage at the beginning, but that's due to the emulated Android starting up initially, so this can be ignored. The actual app performance starts at where it says main activity. From there, you can see when the listen button is pressed, this being the pink lines on top. From the profiler, we can see that there is barely any CPU usage and only about 77.6 megabytes of memory usage, along with minimal to no network usage and very light energy usage.
So here's, excuse me, here's a demonstration video of our project.
This is the Hearing with Eyes capstone project.
So as you can see, Will was running that mask there that we had developed over the past semester. And then it also, when Will spoke into it, it said that it transcribed the speech, and that would be used in an environment where masks have to be worn.
So in general, the only code that we had to abide by was of Bluetooth, and specifically IEEE 802.15. Bluetooth allows for the connection of up to 7 devices using a master-slave architecture, but we didn't hit that constraint as we only have one master and one slave in our connection. And unlike a Wi-Fi based solution, Bluetooth allows for minimal configuration to improve, as Wyatt said, accessibility, which is one of the main factors in this project. And then Bluetooth Low Energy allows for a similar range and other features from the standard, while reducing power consumption and cost, also making it more accessible. And in general, we found that Bluetooth Low Energy wasn't a limiting factor in the project.
So as I had mentioned before, the big thing driving our project is the API that Google has trained. And in doing so, we have to ask, where does that data go? Since it is a cloud-based speech-to-text algorithm, it reuses neural nets which are dependent on more and more data. So we have to be responsible in telling our users that their data will be collected, it's going to be used somewhere, and making sure that we're respecting people's privacy and abiding by privacy rules and laws. And additionally, prioritizing costs is also an ethical issue. At a larger scale, we can make this pretty cheap, as that is one of our big requirements for this project, since we want it to be accessible. But at what human and labor cost does that cost prioritization come in?
For engineering complexity, the main things we faced in software engineering side was dealing with Android Studios. The software team worked heavily with Android Studios to develop the app. For the hardware team, we went through the different iterations for the battery to, first of all, get the smallest we could into the mass to reduce weight, and also have it still last a sufficient amount of time that it's not annoying for the person. But one of the more unique challenges was actually putting it together, the mask, to make it still desirable to wear, which overall was actually really successful. The total weight of the mask with the hardware inside is 35.4 grams, which is less than what a face shield would be, which is usually above 70 grams. So in terms of wearability, it's really comfortable, easy to use, and easy to set up.
So starting to wrap this all up, we consider our project a success. We set out to create a mask to aid the hearing impaired, and we were able to do so. But that certainly did not come without hurdles. For example, Kevin and I on the software team, we had to take a deeper dive into Java than we've had experience with. And the hardware team has had to take a deeper dive into working with microcontrollers than they have before. And then, of course, as I'm sure every other capstone group this year has encountered, time and meeting restrictions to make sure everyone's staying safe and healthy. Further down the road, if we towards refinements, we'd want to do better signal processing, possibly with an RN-52 microcontroller. This is sort of an all-in-one, simpler solution. And also, most importantly, circuitry protection to protect all of the circuitry inside of the mask from humidity or any other bodily fluids coming out, since it is in a mask.
So, like we said before, cost and accessibility were a very big part of this project. And as you can see, we were able to get the total cost parts out under $30, with the most expensive component being the Arduino Nano. And in general, we would hope that you would be able to see this on like a retail shelf for about $35 to $40, making it pretty accessible to most people.
Here are references for our presentation. And at this point, we will take any questions.
Thanks, guys, for your presentation.